Now you may worry that the fixed point is messed up by this presence of the boundary, but so I want to separate those two things. So just given a fixed point, then this goes through, everything gets reduced to finding the classical fixed point. Good question. But we can we can actually do better. We can actually construct the unitaries. Here's how it works. So there's again two steps to this procedure. One's the rewiring, and then the shrinking. So let's do the rewiring first. So the goal is to find a unitary transformation that takes the state of this, of these. So there's a spin here. There's a domain wall here, a domain wall here, a domain wall here, a domain wall here, and a domain wall there. There are 5 domain walls, and then 1 extra degree of freedom, which is in a product state, which is not shown. And over here, similarly, there are 5 domain walls, and then 1 extra degree of freedom, which is not shown. And so the idea is I'm going to take the state of these domain walls with their appropriate square root of weight factors. We're going to find a unitary U1 that turns this into the same state, but now with S's, these tensors S, involving the state which was previously a product before, and which puts the original sort of link here into a product state. That's the unitary we want to find. And I claim that this unitary here solves that equation. So the action of U1 on this basis state is given by a sum over all F of the same basis elements here and some particular amplitudes that depend on S and T. And you can check this unitary is not doing much. In a sense, the A, B, C, D elements are all controls. They just control what happens to the other degrees of freedom. They don't ever get acted on themselves. They're always left invariant by the unitary. So ABC over here is ABC over here. You're not summing. But you do change the state of E and F. So it acts just on the E and F degrees of freedom and leaves the A, B, C, D alone. And you can check that if you ask, is this transformation actually unitary? It's obviously a linear transformation, but is it unitary? Then its unitarity is implied by the fact that SS equals TT. So the classical RG, part of the classical RG fixed points equation implies that this U1 is unitary. Okay. Now, similarly, we have to also do this transformation. And here we have a bunch of S's, 3 S's, and 6 domain walls, 6 degrees of freedom. So that's this side over here. I mean, we're going to turn that into a single T and 3 auxiliary degrees of freedom that are now in product states. So I want to remove some degrees of freedom. And so in equations, what we want to do, this is again a little piece of the total wave function. So there's a T ABC for these 3 links. There's also T's from adjacent links that we're not going to worry about. So that's these adjacent T's. There's ABC, and then there's a 0, 0, 0. And then there's the state on this larger complex. So again, you have now 3 S's. Here's 1, 2, 3, and then the same T's, which correspond to the domain walls out this way. And you have these 6 degrees of freedom. So now we want, again, a unitary U2 that takes this wave function and turns it into this wave function for all values of the unlabeled parameters. So for every choice you can make of the degrees of freedom over here, you want this equation to be true. And now again, I claim there's a relatively simple solution that is where again, A, B, C are like control degrees of freedom. So you apply U2 to A, B, C, 0, 0, 0. You get a sum over the remaining degrees of freedom, D, E, F, with some amplitude, which is a ratio of 3 S's to 1 T. The A, B, C degrees of freedom are unchanged. They're control degrees of freedom. And then the D, E, F, you get some amplitudes. And again, I claim that if you use the equation SSS equals T, you can verify that this transformation is unitary. And I emphasize this transformation is not completely fixed by this equation. There are matrix elements of U2 that are not specified, but you can fill them in however you want and not affect the transformation here.
This is a gap system or not?
No, this is gapless.
This is gap.
Yeah.
So this is very similar to CFT.
It's similar, but
Yeah.
not exactly the same. Yeah. Yeah. So these are the explicit unitary transformations that do the mapping. So given the classical RG fixed point, I can construct a quantum state which is a quantum s equals to 1 fixed point. So that's the message here.
Just one confusion.
Yeah.
How do I know that these S and Ds exist?
You don't. Okay, you don't know they exist. In fact, there's a subtlety here. This scheme is, I'm a little bit cheating because this scheme doesn't actually have a fixed point at the classical fixed point. You have to make the S and T keep getting larger and larger. But they grow very slowly with system size, so you can always cut them off. So I didn't talk about this, but we'll discuss it carefully in the paper. But you can always do an approximate version of this, where you have some approximate tensors and an approximate fixed point, and then show that there is an approximate wave function, which approaches the true wave function with unit overlap and thermodynamic limits. So everything can be done in this approximate way. Or you can use an improved RG scheme, where again you can actually find there's a true fixed point.
So in particular for the Ising state that you wrote, I only have some approximate versions of these S and Ts.
Yeah, exactly. For any given system size, you can have a very good approximation to a fixed point, but technically in this scheme, it doesn't quite give you an exact fixed point. So this is the simplest version, and in fact, you can easily improve upon this. Okay, so let me wrap up with this section with some comments. Okay, this is just what I was just saying to you, Janet. This TRG is only one of many schemes. Many people here are experts in these kind of tensor contraction methods. So there are ways to do this in a more thoughtful and systematic way. And each of these sort of rewiring schemes can be easily adapted, at least all the ones I'm aware of, can be easily adapted to produce this S equal to 1 fixed point. So the basic point remains we can now show for this infinite class, not just Ising, put in Potts or put in, whatever you want. Any critical wave function, any critical statistical model turns into a critical quantum state where we can show that there is this fixed points RG structure. Yeah.
So you mentioned that so that to describe a Gabriel's state looks like the fixed point tensor has to be infinite dimensional.
Yeah, for this scheme it needs to be technically infinite dimensional.
But you say that the dimension it may grow as a log of a system.
Yeah, it grows very, very slowly. So like one statement I can make as if you want like a complexity statement is that there is a polynomial bond dimension PEPS which has unit overlap with the true ground state wave function and thermodynamic limits. So you can prove things along these lines. And in fact, yeah, as I said, if you use an improved RG scheme or maybe an actual fixed point is possible, where you remove some correlation or something like that first, then you can have a true fixed point where it may be infinite dimensional, but it's not growing with system size. So this is a Hamiltonian, which I didn't show any calculations, but we're actually doing numerics right now. That's the part which we haven't finished up yet. Where this is a Hamiltonian, which is interacting critical theory in more than one dimension, which we can essentially solve and calculate critical exponents of. So this is a essentially solvable interacting critical theory, quantum critical points. And there are not so many of those in the world. So I think that makes this an interesting construction. And very interestingly, just like yesterday, there was a way to construct these unitaries without actually variationally optimizing anything. If you knew this path in Hamiltonian space, you could make the unitary directly from that path. Here too, we don't actually ever have to do a variation calculation. There's a way just from the local data to construct a unitary transformation. Right, I actually showed you how to do it. You solve this SS equals TT, which is some kind of like local equation, and then you use that to build the unitary directly. So again, this hints that there's a much wider world where there's a kind of non-variational way to think about these tensor network algorithms with this RG character. Okay. So that's what I wanted to say about the square root states. So now let me go to the final part, where I'm going to talk about some looser collection of ideas which flow from what I've told you about so far, and what we're doing next.
Excuse me.
Yeah.
So you mentioned yesterday that you can describe a Fermi equilibrium
Yeah, wait like 5 slides,
I see.
and then I'll, yeah. Yeah. Okay, so what have we done so far? I've now shown you that for many, many kinds of gap systems, for an infinite class of gapless systems, we have this S source structure. I just finished telling you about the classical square root states. And now I'm going to tell you about other kinds of phases in an attempt to convince you that this is an extremely general construction. I'll talk about CFTs. I'm going to finally talk about the case of S greater than 1 with a gap, what that looks like, Fermi surfaces, talking about a little bit about area laws, just a little bit of quantum gravity, because why not? Quantum gravity is fun. And then at the very last, I'll comment on algorithms and try to recruit you to help me with this set of problems. Okay, so CFTs. So, okay, what should CFTs be? What S? It's a quiz. S equals 0. Anyone think it's S equal to 0? S equal to 5? What about S equals to 1? Yeah, okay. Right, because, yeah, S equal to 1, right? Okay, that's right. CFTs are S equal to 1. We conjecture. And some evidence for that is that in some sense they're actually as entangled as topological liquids. They have the same kind of entanglement structure. They have subleading universal terms. And then correlations are very easy to include in these networks. You know, this RG structure naturally encodes long-range correlations, as I just showed in detail with the square root states. So the square root states have less entanglement than CFTs in a certain precise sense. For example, if you have the square root state and you look at 2 distant regions, those regions have no entanglement. So there's no long-range entanglement in that state in a certain precise sense. Whereas the CFT, you can always violate a Bell inequality with 2 spins far away. So CFTs are slightly more entangled, but nevertheless, I showed you that you can include both entanglement, that comes from the topological liquid, and you can include long-range correlations, that comes from the square root states. So it's hard to imagine that for some reason CFTs just doesn't work for them. And in fact, although I won't talk about them here, we're very close to some rigorous results in 1D, and I think higher dimensions won't be too far behind, where we can actually just rigorously prove that CFTs are S equal to 1. Regulated lattice models, which realize the conformal field theory and flow energy limit, have S equal to 1. But I don't want to just stop here. I want to give you a kind of sketch argument for why you should think this is true. And I'm going to call this the de Sitter sketch argument, or argument sketch. And the idea is the following. So this is de Sitter space in some coordinates. It's a uniformly expanding universe. So there's some time coordinate eta, and there's a space coordinate dx squared. This is the space part of the metric, and then there's an overall factor of 1 over eta squared. So everything gets bigger as eta goes to 0. And there's a length scale here called the de Sitter radius. So this is actually not a bad approximation to the metric of our universe right now. And if you put a CFT into such a space, then because it's a conformal theory, and because this metric is conformally equivalent, that means proportional to a flat metric, then the CFT does not, in a sense, see this conformal factor. It doesn't care about the eta squared. So here's a precise version of that. So the simplest CFT you can think of is a free scalar field. However, you can't just put the usual connection. You have to do what's called conformal coupling. So there has to be a curvature coupling here in order to ensure that it's actually a CFT. So just a scalar field without the conformal coupling is not a CFT. It's gapless, but not a CFT. So you have to put this curvature coupling in with some particular constant k, which depends on the dimension. And then if you insert the de Sitter metric into this action for this scalar field, and you do a little calculation, you'll find that what you get out, you make a field redefinition, so you absorb some factors of eta. Then you get out an action for this field chi, which is just the action of that field in flat space. So there's just a field redefinition where this becomes just a theory in flat space, nothing's happening. So obviously the time evolution as a function of eta doesn't do anything. The ground state of this field chi as a function of eta is just invariant. It's the ground state. Yeah.
So the curvature coupling term is to it's because you construct it in the de-Sitter space, is it right?
Yeah, I mean, so, yeah, what this means is, I mean, what this, you're saying this is saying that if I put it on an arbitrary manifold, that in order for it to be a conformal field theory, it has to have this coupling to the curvature. And then in de Sitter, this curvature coupling cancels a certain cross term that comes from here, which would otherwise give you a mass and change the story. So that's why, if you didn't tell us, there'd be a mass term here, and it would look not the same. Okay, so this is completely standard, nothing new here. And so, in a certain formal sense, the continuum limit CFT wave function is completely invariant under changes of size, which is not surprising. It's a CFT. But that's sort of an unregulated statement, so it's not something you can make very sharp in terms of a lattice model, for example, or some quantum information context. So we'd like to regulate this statement. And heuristically, what you need to do is to make some UV, some irrelevant deformation. You need to change the high energy physics and leave the low energy physics the same. But adding such a high energy only deformation is sort of like adding a gap theory. It's like adding something that only changes the physics at energy scales above some fixed scale. And so you might imagine, at least heuristically, that you can use the gaps machinery of the previous talk, or I could put a gap system inside an expanding universe and construct an exact transformation which mapped it from one size to the next size. You might imagine you can use something like that machinery to sort of prove that the deformation, the irrelevant deformation away from the CFT itself is S equal to 1. The CFT is sort of also S equal to 1, and so together they're also S equal to 1. So that's not a rigorous argument. It's not even a precise argument, but it's a kind of heuristic for why we would believe that CFTs are in this class. And we're working hard to make something like this argument work, and I think it's possible. So what about gaps with S greater than 1? Well, there is a trivial answer to this, which we call the layer construction. And the layer construction works like this. You take for example, integer quantum Hall state, which lives in 2 dimensions and has S equal to 1, as I showed you yesterday. And you make a 3-dimensional system by just stacking a bunch of these integer quantum Hall states. And in particular, you demand that things be kind of isotropic. So if this is L by L, then this is L layers. So it's a kind of homogeneous, it's a sort of isotropic system in the sense that every direction is L. And if we demand that our RG transformation expand all directions the same, if it increases sort of the in-plane directions by 2, but also the number of stack by 2, then this system is S equal to 2. 3 dimensions. And here's the picture for what that is. Start with integer quantum Hall state, a 2-stack system on some small size. First thing you can do is double the size. That can definitely be done with a local unitary transformation. Right? So now I've doubled the size in the X and Y plane, but I haven't doubled the size out of the board. To do that, I need to have a second copy, because I can't make 2 copies of the integer quantum Hall state from nothing. So I need to have some other integer quantum Hall states of some size nearby. So I bring in my second copy, I expand it up 2L by 2L, and then I just rifle these 2 things together in the standard way, like with a deck of cards, to make 4.
So in terms of classification, this state should be trivial, right?
So what do you mean by trivial?
Just the classification of all the Fourier entangles and SPD.
So this state is invertible, for example.
Yeah, but so in 3 dimensions, there's no non-trivial invertible state. In 3 dimensions. And without any symmetry, there's no non-trivial.
No, I mean, isn't this an example of a such a thing? It's just a layers of integer quantum Hall. You can't get rid of integer quantum Hall.
I know, but if I use a 3-dimensional system, the 3-dimensional system is a trivial state.
What's the path to a trivial state?
Sorry?
What's the path to a trivial state?
It has some autonomy between the layers.
But why would that just makes the Chern number get bigger?
No, wait. See, there's no 3-dimensional invertible state without any symmetry. Based on the classification.
answers to this. One is that it's s equals 2. It could also be s equals 0. It doesn't imply there's not a better path. So it doesn't rule out that it could also be s equals 0.
Oh, okay. You said, oh, okay. It could also be s equals 0.
It could also be s equals
If
0.
you do another kind of RB or something.
Yeah, exactly. But an example where it won't work is if you put, instead of integer quantum Hall, you put Z2 topological order. So then if you put Z2 topological order instead of integer quantum Hall,
Yeah.
then this stacked system is indeed non-trivial. It has a ground state degeneracy which grows with system size.
Oh.
So that's maybe a better example, if you like, where there's definitely no way to trivialize it.
Yeah.
And so actually that's a simple example of a situation, a trivial example in 3 dimensions of using this layer construction where I stack layers of Z2 gauge theory, of toric code in 2D, of an S greater than 1 system, and indeed trivial has a ground state degeneracy which grows with system size because you just get 4 states for every copy. So you get 4 to the L. Okay, but as I said, this is sort of a trivial example. We may wonder if there's anything non-trivial. And indeed, actually, there is something highly non-trivial, which is called Haas code. So what is this thing? It's a system in 3 dimensions, defined on a cubic lattice with 2 qubits per site. The Hamiltonian is the sum of commuting projectors defined on cubes. So I'm not going to show you the Hamiltonian. It's just a bunch of x's and z's. It's not illuminating, but you can look at his paper. It's stable and gapped, but it has a ground state degeneracy which depends in an unusual way on system size. So for example, whenever the system size is a power of 2, the number of ground states is 4 to the linear size of the system. If it's some power of 2 plus 1, then it's 1 ground state, I think. Ha has a number theory formula for it tells you what the ground state degeneracy is. And if you want to go from one ground state to another, if you're in a topological state, the way you do that is, for example, to wind an anion around the system. But in Haas code, those so-called logical operators, which move you from one ground state to another, are actually fractals. So it's like supported on a Sierpinski triangle or Sierpinski gasket. So it's a very, very peculiar system, but with no obvious pathology. And Ha showed that actually his code is S equal to 2. So you need 2 copies of the system at size L to make 1 copy at size 2L. And in fact, what he showed is that it's something called branching Mera, which is sort of an older version, or a sort of independent version of, and related to the S source RG, but not as general. But for this case, where it reduces to an exact circuit, and does the same thing. So this code exists, and it's weird. It sort of looks like a glass. It doesn't equilibrate very well because of these fractal operators. We don't understand it very well. It's very interesting, and it just shows you that there's potentially a really crazy world out there of gapped phases with S greater than 1. Nevertheless, they do fit into the S source framework. So we don't know of anything which doesn't fit into this framework right now in higher dimensions. So what about gapless with S greater than 1? Actually, here it turns out it's much easier and much more familiar. And the conjecture is that Fermi surfaces, so just ordinary metal, is an S source fixed point with S equal to 2 to the d minus 1. D is a spatial dimension. So in 1 dimension, this is S equal to 1 because it's just Fermi points, so it's essentially a CFT again. In 2D, this is S equal to 2, and in 3D, S equal to 4. And the heuristic argument for this actually starts from the CFT result, because it says one way to view the Fermi surfaces as a bundle, a collection of 1 plus 1 dimensional CFTs. So there's a bunch of chiral fermions that run along the Fermi surface. This is a completely standard perspective. So at every point on the Fermi surface, you have a fermion mode which goes radially. So you kind of have like a one-dimensional mode for every point on the Fermi surface. And now we said each CFT, each such one-dimensional mode is S equal to 1. And now we need to count how many such modes are there. Well, in a Fermi surface in a size L box, there's L different K points. So there'll be roughly KFL to the d minus 1 points on the Fermi surface. So that's roughly the number of independent, the number of K modes you can have. And so if I want to double the system size, then I'm going to have to change this number of modes by a factor of 2 to the d minus 1. And so it's very much like the layer construction again. I'm just adding a bunch of extra, in this free fermionic case, it's literally layer construction. It's just a bunch of decoupled modes. I make them bigger, I add more modes, so I need a bunch of extra copies. Just where I need 2 to the d minus 1 copies. And this is very satisfying because, as I showed you on the very first talk yesterday, when s is equal to 2 to the d minus 1, then the entropy recursion formula gives you a logarithmic violation of the area law, which is exactly what these Fermi surfaces have. So everything looks consistent with Fermi surface being s equal to 2 to the d minus 1. And I think once we know how to prove it for CFTs, we can probably tackle this problem as well to get a rigorous demonstration. But for now, I think it's a very plausible conjecture. So what about a general area law for gapped faces? Is there any way that we could say something more general? You know, I already told you the weak area law. You have a unique ground state, then there's an area law. I said topological states have an area law. In fact, it's easy to show from the S source framework that everything from s equal to 0 up to s equal to 2 to the d minus 1, all these states automatically obey the area law, just from the recursion relation. So that leaves states with s equal to 2 to d minus 1 and states with larger s as possibly violating the area law. It turns out you can rule these states out with a thermodynamic argument as long as you make an extra assumption, which is that if you assume that the low temperature free energy decays exponentially, so that is the low temperature free energy behaves like a very reasonable assumption for a gap system. If you make this assumption, then you can prove that the ground state can violate the area law no worse than logarithmically. And actually the way it works is very clever. This is due originally to Hastings. We generalize it for our paper, but Hastings had the original idea. You take a thermal state, and you choose a temperature which is low but not so low. That is, it goes to 0 logarithmically with 1 over system size. So as you make the system size large, this low temperature suppresses all the excitations, so that this thermal state becomes very, very close to the ground state. But because of the thermal state, it's easy to bound the mutual information between two regions. You can actually prove that it's bounded by the coupling constant of the Hamiltonian divided by the temperature times the area. So all thermal states of local Hamiltonians obey an area law for mutual information at all temperature. So now you see, if I put in T equals this, then I get area log L. So I can't have a worse violation. So with this assumption about the free energy, and using this kind of trick to approach the ground state sort of with a low temperature, with some slightly going to 0 temperature as system size increases, you can actually show that the mutual information can never be worse than area log L, and then you can then convert that to a statement about the entropy itself in the ground state. So this is all in our paper. You can look at the details there. So it seems like you rule this stuff out. You rule everything out down here that obeys the area law. So the only dangerous case is this s equal to 2d minus 1. So could there be some kind of Fermi surface-like system, but with a gap? You know, with as much entropy as a Fermi surface, but with a gap. And I won't go through it here, but just point out to you that we ruled out, or we gave an argument that this is also impossible. So we derived a novel bound, which is that the entanglement entropy should be less than the logarithm of the ground state degeneracy. And very, very briefly, the way that works is as follows. Suppose I'm looking at some state of some region, rho A. And I can consider another state, sigma, which is